We now begin studying multiple integration. We do so by first considering double integrals. We'll start by looking at double integrals over a rectangular region, and then in the next video, we will extend that into a more general region. So we consider a continuous function, f of xy greater than or equal to 0, defined on some closed rectangle R, given by AB crossed with CD. So what this is this is the set of all points x, y, such that x between A and B inclusive, and y is between C and D inclusive. So as we can see down here, x ranges from A to B, y ranges from C to D, and our region R is this entire rectangular region. Now the graph represents a surface that's above the xy plane that has equation z equals f of xy, where remember z represents the height the surface is at the point xy. So it's the height above the xy plane at the point xy. Now let S be the solid that lies above the rectangular region and under the graph of F. So it's this lightly blue shaded region right here. This is our solid. Base of the solid is R. So our goal is to find the volume of this surface S. So to do this, we divide R into small rectangles, R sub ij, each with area of delta A and with sides delta x and delta y, as we did here. So this was our rectangular region here, and we just divided it into subrectangles. Each one is R sub ij. So this is done by dividing the interval AB into m subintervals of equal length delta x, and by dividing the interval CD into n subintervals of equal length delta y. So we take the x-axis, the A to B, and we're going to divide that into however many subintervals we want. Right? And we in such a way that each subinterval has the same width delta x. Then we do the same along the y-axis between CD. Now this m and n does not have to be the same. Right? So delta x and delta y don't have to be the same. It's just each of these distances here are the same. So each delta y would be the same, and each delta x is the same. So this would give us that delta x is b minus a over n, and delta y is d minus c over n. And of course, delta a would be delta x times delta y, right? The area of a rectangle is length times width. So the volume of the thin rectangular box Rij, so we're going to take a look right here. Look at this, right? So it has, let's say that's length delta x, height delta y. So its area is delta x times delta y. So now the volume of the thin rectangular box above this, so of this subrectangle here, is f of x sub ij star comma y sub j star times delta a, right? Remember, its area, volume is area of the base times the height. So this f of x ij star y ij star represents the height within this box. So the point xij star yij star is just some arbitrarily chosen point within this subrectangle R. And I'm sorry, I should have had down here sub ij. Now, using the same idea for each of these subrectangles, right? So that was only for this subrectangle here. We do the same thing for every single subrectangle we have. We obtain an approximation for the volume of S given as a double summation. So it's the sum from I equals 1 to m of the sum from j equals 1 to n of f of x sub ij star y sub ij star times delta a. Now this is known as a double Riemann sum, and it can be used to approximate the volume of the solid. So here, what this double sum is saying is that for each subrectangle, we evaluate the function at the chosen point, multiply by the area of each rectangle, and then add up all of those results. So as is the case in single variate integration, we can obtain a better approximation to the actual volume if we let m and n become really, really large. Specifically, we want them both to approach infinity. Now, we'll use the notation here to represent the maximum between delta x and delta y. Then, as mn approaches infinity, this value will approach 0. Then the volume would be given as the limit, as the maximum between delta x and delta y approaches 0 of the double Riemann sum. And we define this to be the double integral as well. And so here's our formal definition of the double integral. So I'm going to point out here that this is how it's represented. Right, double integral. This represents what the region that we're integrating over, in this case, over a rectangular region. Now, we can think of the double integral as a signed volume, just as we thought of the single integral as a signed area. And just like single integrals, double integrals also have several properties. Right? So the first one is if you're to double integral of a sum or difference of functions, it is just the sum or difference of the double integrals. If you take the double integral of a constant times a function, then it's just the constant times the double integral of the function. If our region is the union of two regions that do not overlap except possibly at boundaries, then we can write the double integral over the region R as the sum of the double integrals of each individual region. If f of xy is greater than or equal to g of xy for every xy in the rectangular region R, then the double integral of f over R would be greater than or equal to the double integral of g over R. And finally, if f of x is a function that's bounded below by some number little n and above by some number big N, then this little n times the area of the region will be less than or equal to the double integral of f over the region, and that would be less than or equal to this big N times the area of the region. And this one is one of the more important ones. So in the case where f of xy can be factored as a product of single variate functions g of x and h of y, then over the rectangular region AB cross CD, the double integral over that R can be written as a product of single integrals. The integral from A to B of g of x times the integral from C to D of h of y. Now, if you remember when you studied single Riemann sums, it was really difficult to actually calculate the integral using the Riemann sum. So what we need to do is look for a simpler way to evaluate it. And we're going to do the same thing here with double integrals. And the basic idea is to write the integral into two single integrals, one for each of the independent variables. Such an integral is known as an iterated integral. So an iterated integral for the function f of xy over the rectangle AB cross CD is an integral in one of two forms. Either the integral a to b, integral c to d of f of xy dy dx, Now the interpretation of this first form is we're integrating from a to b the integral from c to d. So we're going to take the integral from c to d f of x, y first, then integrate that result from a to b with respect to x. Or we can flip the order. Integral from c to d, integral a to b, f of xy, dx dy. So this interpretation here is, first, we integrate from a to b, f of xy dx. Then integrate that result from c to d with respect to y. Right, and that's summarized in this sentence down here. So this leads us into what's known as Fubini's theorem, which will be the most important theorem of this video. And it says, suppose that f of xy is a function that is continuous over a rectangular region R equals AB cross CB. Then the double integral of f over the region R is an iterated integral. So this double integral over R of x, y, dA, is either the iterated integral AB, integral CD, dy dx, or you can flip the order, integral CD, integral AB, px dy. Now, this is true also if f is bounded on R, f is discontinuous only on a finite number of continuous curves. In other words, this must be true, or in order for this to work, f must be integrable over the region R. And now we're going to close out by looking at several examples, or in this case, actually 2 examples. So we're going to take a double integral over the rectangle 0, 2 cross 0, 3 of 3x squared minus y dA. First, by integrating with respect to y first. Then we'll switch the order of integration. All right, so first, we want the order dy dx. So this integral dA by Fubini's theorem will be the integral from 0 to 2, integral from 0 to 3, 3x squared minus y. First with respect to y, then with respect to x. So just as with partial differentiation, when you're integrating with respect to a specific variable, you will treat all other variables as a constant. So the integral of 3x squared with respect to y is 3x squared times y. And then we'll have minus y squared over 2. And this is evaluated y equals 0 to 3. And then we'll integrate that with respect to x. Right, so we'll have the integral from 0 to 2 of 9x squared minus 9 halves, and then with respect to x. So now we can just integrate this like normal, so we'll have 3x cubed minus 9 halves x. This is evaluated x equals 0 to 2, and when you evaluate that, you get 15. So now we're going to go ahead and flip the order. So we're going to integrate first with x, then with respect to y. So let's just get rid of all of this. And so I'm just going to get rid of that. So it'll be dx, dy, and then of course I have to change the bounds as well. Right, so it'll be 0 to 3, then 0 to 2. So now we'll get the integral from 0 to 3. So we'll have x cubed minus x times y, evaluated from x equals 0 to 2. So I have the integral from 3 of 8 minus 2y. So it's 8y minus y squared, evaluated from y equals 0 to 3. And when you go ahead and evaluate that, you find that once again you get 15. So the order in which you integrate does not matter. However, it could be more convenient to do a specific variable first. And as we'll see in the next video, when we're looking at more general regions, flipping the order of integration sometimes is a lot more involved than simply switching bounds like we did here. And we'll deal with that in the next video. For now, let's go ahead and take a look now at integrating x sine of xy over the rectangle 0, 3 cross 0, 2. So first express it as an iterated integral using both orders. Then we'll decide if one order is easier to integrate than the other and use that order to actually evaluate. So using Fubini's theorem, this double integral would be the integral from 0 to 3, integral from 0 to 2 of x times sine of x times y, dy dx, or could have the integral from 0 to 2, integral 0 to 3, dx dy, right? So we can integrate either with respect to x first or with respect to y. Now, if we take a look at this, if we integrate with respect to x first, we would have to do an integration by parts, right? Whereas if we integrate with respect to y first, it's just simple u sub. So we're going to integrate with respect to y. That's the more convenient method. That's the easier method. 0 to 3, 0 to 2, x sine of xy, dy dx. So our u would be x times y. Our du is then x dy. Oh, look. So we're going to be left with the integral from 0 to 3 of negative cosine x times y, evaluated y equals 0 to 2. So we'll have the integral from 0 to 3 of negative, I'm going to write it this way, of 1 minus cosine of 2x dx. Right, so this would give us x minus a half sine 2x evaluated from x equals 0 to 3. And when you evaluate that, you get 3 minus sine of 6 all over 2. And that would be our double integral. So this is just an introduction into double integrals. This kind of introduces the idea of a double integral, as well as introduce some of the notation. What we're going to do in the next video is we're going to take these concepts and extend it into a non-rectangular region. So we're going to look at a more general region. And we'll see how we can integrate. So maybe a region that looks like this, right? And we'll see how we could integrate a function over a region that is defined in such a way. So that will conclude this introductory look at double integration.